Our story starts with a guest entering a hotel. It's called the Hilbert's Hotel. He walks up to the reception, where the desk clerk greets him. When he asks for a room, the clerk regretfully informs him that the hotel is all booked up. Which is curious because the hotel claims it always has rooms available. And so, as the guest turns to leave, the desk clerk then informs him that there is a room available. That's because the Hilbert Hotel doesn't merely have hundreds of rooms. It has an infinite number of them. Welcome to the Maths Factor. This episode focuses on mind-boggling, definition-defying ideas in mathematics. Besides the magic of infinity, we also take a quick look at irrational and negative numbers. Our journey takes us through India, Greece, and into the fascinating Hilbert's Hotel. So keep watching as we whisk you into the magical world of numbers. Back to Hilbert's Hotel. Our clerk needs to make a room free for his new guest, but all the rooms are occupied. Luckily, the hotel has infinite rooms, so he shifts the occupant of room 1 to room 2, room 2 to room 3, room 3 to room 4, and so on. That frees up room 1 for the guest and accommodates everyone else as well, although inconveniencing them by the move. And as our first guest settles in, let's open the next chapter in our Hilbert saga. Next up, an infinity of guests arrive. They trudge into the hotel, all hot and tired. What will the desk clerk do, faced with this endless line? Here's his plan. He moves the occupant of room 1 to room 2, room 2 to room 4, room 3 to room 6, and so on. This doubling trick opens up all odd-numbered rooms. Let's look at this in a little more detail. Take room number 4. The occupant will be shifted to room number 8, but then room 4 will be taken up by the occupant of room 2. So all even rooms will be occupied. Now take room 5. The occupant will move to room 10, but 5 will stay empty, as well as all the other odd rooms, infinitely many of them for our infinity of guests. Now, an even more complicated situation arises. Later that day, still more buses, each loaded with infinity of guests, arrive, demanding that the hotel live up to its motto, "There's always room at the Hilbert Hotel." Any idea on what is the solution to this infinite problem? I'm going to tell you, but first let's explore some other ramifications of this infinitely fascinating concept. Let's start off with two little boys, Vihan and Arman, who are playing with cars. One says, "I have 100 cars." The other retorts, "I have one more." It continues, "I have one more than that." It's a conversation that could go on and on. But what the children have grasped is that there is always one larger number. It's a simple understanding of infinity, that we can keep adding a number endlessly. Here's a second conversation. Vanya is sitting with her mom, who asks her how much she loves her. Expansively young Vanya replies, "From here to the moon, to the stars, to the next galaxy, and more than that." This is not just a cute scene. but shows that children intuitively have an idea of enormously large numbers, larger and larger numbers that could go without an end, which points to the idea of infinity. Now, this is the symbol of infinity. It was the mathematician John Wallis who in 1650 suggested this symbol. It looks a bit like an 8 turned on its side, doesn't it? Now, is there any way that we can move beyond the symbol and actually experience infinity? To try that out, Ishan has decided to go shopping. Really? First off, Ishan picks up some fun accessories. He then heads to the mirrors to check himself out. There is a mirror in front and behind. And these open infinite vistas to Ishan. Quite fun, isn't it? You could try it out on your next shopping trip. Now, infinity is a concept baffled many mathematicians. Another curious idea that shook many of their beliefs was the idea of negative numbers. Now, what are these? Very simply, it's a number less than 0. Let's look at it in terms of money. I have 500 rupees. I spend 100 on clothes, 200 on food, 200 on transport, and another 100 for medicines. Oops, I seem to have overspent, right? My bank would call this an overdraft. In mathematics, we call this a negative number. If we represent this idea on a number line, having money is positive. As we spend, we move down the line till we go into negative, which means we owe money. Another simple way of visualizing this is on a thermometer. It's a cold day. The temperature is about 3 degrees centigrade. And the forecast tells you it's going to drop 4 degrees. Which brings us to a temperature of -1 degrees. Now, the first understanding of negative numbers was in China. The Chinese used red rods to represent positive numbers and black rods to represent negative numbers. These were used for commercial and tax calculations, where the black cancelled out the red, leaving either a money balance, which was positive, or a deficit that was negative. But it was Indian mathematician like Brahmagupta who in the 6th century developed consistent and correct arithmetical rules on the use of negative numbers. Brahmagupta called positive numbers fortunes and negative numbers debts and came up with a whole series of rules. Now, the Greeks like Diophantus pooh-poohed these ideas and called negative numbers absurd and impossible and completely ignored them. They couldn't see how a negative number could be meaningful because it was not possible to have a quantity that was less than nothing. This opinion was passed down to later mathematicians in Europe. Even in the 18th century, the British mathematician Francis Messerus claimed that negative numbers darken the very whole doctrines of the equations and make dark of the things which are in their nature excessively obvious and simple. Now, this reaction fades into nothingness compared to the reaction to irrational numbers. Now, what are these? Very simply, they are numbers that cannot be expressed as a simple fraction. Take this piece of elastic. We take this unit as 1 unit. Now I stretch it to twice its length and mark the original length in it. Then let it contract. This indicates half or 1/2. Similarly, I stretch it to twice its length. I mark the original length. I let it contract. The mark now indicates 1/3 or 0.33333, which stretches on endlessly. But some numbers cannot be represented as a fraction. Now let's see how numbers like this had disastrous consequences for some. For this, we need to move back in time to 520 BC in ancient Greece. We start off with a small boat off the coast of Greece. A man is thrown off the boat and left to die. His name, Hippasus. Now, what did he do to deserve this treatment? Well, the man was a follower of Pythagoras. Pythagoras and his students were great believers in the power of numbers. Their motto was, all is number. And they lived by this motto. Numbers were magical to them. They thought that odd numbers were male and even numbers female. They believed that any aspect of the world could be expressed by an arrangement involving just the whole numbers. 0, 1, 2, 3, and so on. Fractions were accepted, since they were written as ratios of whole numbers. And then, Pythagoras' own theorem changed that world. Wondering how? Well, the theorem famously states that the square on the hypotenuse is the sum of squares on the other sides. Now, when the Pythagorean theorem is applied to a triangle where both sides measure 1, let's see what happens to the hypotenuse. C square is equal to 1 square plus 1 square is equal to 2. And that means C is the square root of 2. Now, when you calculate the square root of 2, you get 1.414213562 and so on, where the digits go on endlessly with no pattern. This is an irrational number. The irrationals were a devastating theory for Pythagoras and his followers. This number jeopardized the cult's entire belief system and was so closely a guarded secret. And Hippasus let his cat out of the bag. He revealed this number and the idea of infinity to the outside world. And for this crime, he had to die. On a journey through infinity, let's meet up with a mathematician called George Cantor, who had some outstanding insights into the idea of infinity. Cantor was born in Russia in the 1800s and was raised in Germany. He gave a stunningly simple proof that showed that the cardinality of the set of subsets of a set is larger than the cardinality of the set, and also revealed that multiple infinities existed, some were larger than others. Cantor worked with set theory to show this, and I will quickly explain what he did, and then let's try and connect it back to Hilbert's Grand Hotel. First, let us see what cardinality of a set means. Very simply, is the number of the elements in a set. Now let's take the set of natural numbers, which is 1, 2, 3, 4, and so on. If we remove all the odd numbers, we get the set of even natural numbers. Here's a question. Which is the bigger set? The set of even natural numbers or all the natural numbers? All natural numbers would be bigger, since even numbers form a part of the larger natural number set. But a one-to-one correspondence will reveal that as far as theory is concerned, the two are equal. Curious, right? And it just gets more so. Let's next look at the set of rational numbers. These are numbers that can be written as a simple fraction. Cantor wondered whether this set was of the same size as natural numbers. Since it is an infinitely large set, he represented it like this. He first lined up all the fractions where 1 was a numerator. 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5. Then he lined up 1s with 2s as the numerator. 2 by 1, 2 by 2, 2 by 3, 2 by 4, 2 by 5, and so on. And then 3 is a numerator, and so on infinitely many times. We're talking about an infinite amount of infinite sets. Now, as we have just showed, if we can show as a one-on-one correspondence with natural numbers, then this set is the same size as the set of natural numbers. At this point, let's head back to the Hilbert's hotel. The hotel which always has a room available for you. Let me quickly refresh your memory. We have a resourceful and mathematically able clerk manning the desk. The hotel is all full up when an infinity of buses with an infinity of tired, sweaty and grumpy travelers arrive at the hotel. He first does the doubling exercise. He moves guests 1 to room 2, guest 2 to room 4, guest 3 to room 6, guest n to room 2n. All the odd number rooms are free, a good start because there are an infinite number of them. Is that enough? Will all the guests really be accommodated? Seems unlikely, doesn't it? Before we assign the rooms, let's visualize all the people we have to serve. So we have bus 1 with infinity of people, bus 2 with another infinity of people, and bus 3 with another, and so on. We can't literally show all of them since the diagram would have to be infinite, but a finite version of the picture is adequate. Any specific bus passenger is sure to come somewhere in this diagram as long as we include enough rows and columns, so everyone is accounted. We now need to devise a scheme for assigning rooms so that everyone gets one. To assign room to everyone, if we zigzag through the diagram in this way, everyone will get covered at some point. So if our clerk starts with passenger 1 on bus 1 and gives her the first room, then second and third rooms go to passenger 2 on bus 1 followed by passenger 1 on bus 2. After serving them, we hand out keys to passenger 1 on bus 3, passenger 2 on bus 2 and passenger 3 on bus 1. If we keep proceeding like this, everyone eventually gets a room. So as advertised, there's always room at the Hilbert Hotel. What we have also worked out is a one-to-one correspondence between the set of rational numbers and natural numbers. Now gear up. We're to get more complicated. All the sets we have discussed so far have been countable, which simply means they have a cardinality equal to or less than that of the set of natural numbers. Even if it would take a, infinite amount of time to do it, every term in the set can be counted. Now, let's move to another set of numbers known as real numbers. This includes all the natural numbers, all the rational numbers, as well as all the irrational numbers like pi, phi, and the square root of 2. Now, these numbers are expressed as a number with an infinite number of digits after the decimal point. Does this set have a one-on-one correspondence with the natural numbers? The way we can prove this is not possible by presuming it is true and showing that it is not possible. It's a method known as contradiction. So let's try and list out all the real numbers. Don't worry, we don't need to write out all the infinite. Let's just write out any 4. Now if we say this is number 1, 0.723904848. And like this, we imagine every real number. To show that I cannot create a one-to-one correspondence with natural numbers, I will create a number that is not in our list. How will I do that? By taking the first number from the number 1, the second from number 2, the third number from number 3, and so on. So the number that will come up with is 0.7430 and so on, because we'll keep proceeding in the same line. Now I'm going to change this number. For the purpose of argument, I will just increase every digit in this number by 1. So I will get 0.8541 and so on. Now this number, which I've just created, will not correspond to any number on my list. How do I know that? See, it won't match the first number because the first digit is different. It won't match the second number because the second digit is different. It won't match the third number because the third digit is different, and so on infinitely. We have created a number that's not in our list. And so we can conclude that this set of real numbers does not have a one-to-one correspondence with natural numbers. Which implies that this is a bigger infinity. And so, if the set of real numbers land up at our Hilbert Hotel, even our enterprising clerk will be at his wit's end. He will have no place for them. We have an infinity that is beyond infinity. Are there still larger infinites possible? We'll leave you with this thought as we come to the end of our episode. We are done with infinity and numbers of all kinds. That's all we have for now, but keep watching the Maths Factor for more intriguing nuggets from the world of mathematics.